Hello everyone, welcome to the video on one of the important article from complex analysis known as a complex integration. So before we start, let me understand what is complex integration first. Okay, what is that complex integration? So here I will write the integral, say I. Suppose I is the integral which is of the form integration f of z dz f of z dz over some curve c, and that C is the closed curve, then this integral is known as a complex integration. So in some cases, there is a circle drawn on the integration to indicate that C, this curve C is a closed curve. Okay, C is the closed curve. So obviously, this Z is a complex variable. As that is a complex variable, the integration f of z dz is known as a complex integration. In uh, in the previous semester you may learn y equal to integration fx dx, okay, or integration fx dx. So that is a integration in real calculus where x and y are real variable, but here z is a complex variable, so it is a complex integration first. So what is that? Z is a x plus iy. Z is a complex variable, so that is a complex integration. Now how we evaluate this integral? Now if we see the actual calculation of integration, this is always a very lengthy or complicated, but with simple example I will explain it first. Let us consider one example. Okay, I will take the example, say we have to evaluate the integral I, which is say z dz. Okay, you may say the answer is a z square by 2, but yes, we are not integrating uh, directly here. We are integrating on the curve C. Okay, and that is known as, also known as a line integral. Okay, so let us assume the curve C is a circle now, and that is given by say C is mod z is equal to 2. So that is the curve. So the answer is obviously not z square by 2, because it's not the integration in a like a real domain. It is in complex domain, and again we are integrating over the curve C. So actually we are integrating in the complex plane, and so this is a real axis x and y is the imaginary axis, and mod z equal to 2. If you see the mod z is x plus iy, so mod z is a root of x square plus y square. Root of x square plus y square is a 2, so this x square plus y square is equal to 4. So actually we are integrating on the circle x square plus y square equal to 4. It is only on the circle, that is on the line integral, that is known as a line integral. So already we know that is uh, x plus iy. So that is a Cartesian form, but yes, we know the equivalent exponential form for x plus iy. That x plus iy can be written as r times cos theta plus I sin theta, and we can replace z by r times e raised to I theta, is it? Because this is a exponential form of the complex number. To integrate this, actually we are converting that in exponential form. We are integrating on the circle, so the value of r should be 2, because over the circle C, the radius is 2, so the value of z we should replace as a 2 times e raised to I theta. If z is a 2 times e raised to I theta, the value of dz will become 2 times e raised to I theta into I d theta, is it? So this is just a derivative. So the integral I will become integration. See, the value of r is a 2 times e raised to I theta. The value of d theta is 2I e raised to I theta d theta, and you will see here the theta is varying over the circle, and to complete one rotation on the circle, the theta will vary from 0 to 2 pi. 0 to 2 pi will be the limits for theta. So this way actually the complex integration is evaluated. And what will happen now? So see here, this 2 into 2 is a 4i 4i is a constant, and this is a e raised to 2i theta. E raised to 2i theta. Base is the same, so we added the power. So e raised to I theta plus I theta is e raised to 2i theta, and the integration of e raised to 2i theta is e raised to 2i theta divided by 2i, and limits are 0 to 2 pi. Now this obviously this 2i gets cancelled and we left only 2, so we left with the 2, and here we have e raised to, if we replace upper limit it is e raised to 4 pi I, and if we replace lower limit, that is e raised to 0 is 1, so that is minus 1. But remember, now again a Euler's formula if we use, e raised to I theta is a cos theta plus I sin theta, so e raised to 4 pi I will be cos 4 pi I, sorry, cos 4 pi plus I sin 4 pi, and cos 4 pi is a 1, sin 4 pi is a 0. So what happens, the value of this term e raised to 4 pi I, the value of e raised to 4 pi I, that will be a 1. The value of this term is also 1, because this cos 4 pi plus I sin 4 pi, cos 4 pi is 1, sin 4 pi is 0, hence it is 1, and now this 1 minus 1, so what happens, the final answer we got as a 0 only. So see here, we started the integral to evaluate. This is one of the simplest integral we taken for explanation purpose. I is integration z dz over the c, and we got the answer as a 0. We got the answer as a 0. But nowhere while solving the examples, we are going to do this actual process, because it's a very lengthy for other examples, obviously, where the integrand is complicated. If integrand is lengthy, then this simplification becomes complicated. So there are two theorems which we are going to use it for getting the value of integral, known as Cauchy's theorem and Cauchy residue theorem. The first theorem is the simplest theorem, says if our function, now what is the f of z here? F of z is a z. We are evaluating this actually, integral fz dz. So if this f of z, if this f of z is differentiable function, if f of z is a differentiable function on and within the boundary, so see this is the circle, this is on the boundary of the circle and within the boundary of the circle, this region. Okay, if on and within the boundary of the circle, if this function is a differentiable, then the value of integral is always 0. So there is no need of any calculation. Whatever we done, we know already f of z is a z and it's a differentiable. Derivative of fz as a z is f dash z is 1. So that is a differentiable function over the entire boundary and inside the circle. Hence, integral fz is a integration fz dz is a 0. So we are not worried about whether it is a differentiable or not differentiable outside the boundary, but if it is a differentiable inside the boundary, the value of integral is 0, and that is our first theorem. And that first theorem says, here I will show you, that is Cauchy's theorem. If you observe, this is our first theorem known as a Cauchy's theorem. And you will observe, if fz is analytic on and within the curve C, then integral fz dz is 0. This is the best theorem for us. Whenever function is a differentiable, straightforward in one line we write it, integration of z dz is a 0. But if the function is not differentiable, if function is not analytic, not differentiable, then we use a second theorem known as Cauchy residue theorem. Cauchy's residue theorem. And for Cauchy residue theorem, whenever it is not differentiable, we have to find out the points where our function is not differentiable. The points where our function is not differentiable in the circle, that points we have to find out, and that is known as a poles here. So how to get the pole? Pole is a point. Pole is a point where the function is not analytic. Not analytic means not differentiable. So here is one example taken. F of z is z plus 2 upon z square, z minus 1 cube, z minus 2 bracket cube, z plus 3, z plus I raised to 4. Then now this function have number of poles, and how to get the poles of a function? Just equate the denominator. Just equate the denominator of a function to the 0, we get a pole. First we get z equal to 0. That is the first point. And that is a pole of order 2. What is the order? Order is nothing but how many times that factor is repeated in denominator. So obviously z equal to 0 is repeated twice. So that is a z is a 0 0 is a pole of order 2. Similarly, 1 and 2, z equal to 1 and z equal to 2, these are the poles of order 3. Next, z equal to minus 3. Z equal to minus 3 is a pole of order 1. And whenever the pole is of order 1, that is also known as a simple pole. And lastly, z equal to minus iota minus I, that is a pole of order 4. So this is the way we can find out the poles, and then we have to check. We have to check how many of these poles, are inside or on the boundary of the circle. If they are inside or on the boundary of the circle, for each of such points, we have to calculate a residue. Okay, and that residue helps us to get the value of integral. Okay, otherwise, if that pole is outside the circle, we should not worry. We should not calculate residue also. So here is a formula to get the integration value. Integration of fzdz over the curve C is a 2 pi I into sum of residues. 2 pi I into sum of residues. So 2 pi I into R1 plus R2 plus Rn, provided these poles are inside the circle. And the formula for residue, yes, this is only the important formula that you should remember, because in examination, majority of the time the question on Cauchy residue is asked, because obviously Cauchy's theorem, if the question is on Cauchy's theorem, on one line you can write integration of z dz is a 0, but Cauchy residue is mainly important, where we have to compute the residue. The residue are at a pole z equal to a, and that pole is of order n, is given by 1 upon n minus 1 factorial. Suppose n is the order of the pole, we start with 1 upon n minus 1 factorial into n minus 1 the derivative. Okay, same n minus 1 the derivative into z minus a raised to n into fz. Means obviously this z minus a raised to n is in the denominator, because of that z equal to a is a pole of order n. So we are just eliminating that factor and we differentiate the remaining term. It is exactly similar in the partial fraction. In partial fraction, when we calculate the coefficient, okay, coefficient constants there, that time we eliminate the corresponding term. Exactly similar, you will come to know while solving the example. We'll take example, it becomes more clear. So let me start here the examples that generally comes in the examination. So majority of these questions are already asked in previous IMA question paper. So here is first question. We have to evaluate integration e raised to 2z upon z plus 1 raised to 4 dz. So let me assume this integral I, which is integration fz dz over the curve C, is the given integral. Okay, given integral. Our aim is to get first of all the poles. Okay, we can say here see, the equate the denominator to the 0, because z plus 1 raised to 4, so it is z equal to minus 1. Z equal to minus 1 is a pole of order 4, is it? We have z equal to minus 1 pole of order 4, and next thing that we have to check whether it is inside or outside the circle mod z equal to 2. See, mod z equal to 2 is set of all complex number whose modulus are less than or equal to 2. Okay, so means if we see the inside region of a circle, so this is z is equal to minus 1. If you calculate magnitude of this complex number minus 1, mod z become 1, and this mod is less than 2, hence it is inside a circle. So z equal to minus 1 is a pole of order 4 inside circle mod z equal to 2. So this should be written. So this is the main first line you should start. Z equal to minus 1 is a pole of order. Z equal to minus 1 is a pole of order 4, which is inside the circle mod z equal to 2. So whenever any pole is inside the circle, we should calculate residue for that. So let R be the residue at z equal to 1. So we'll calculate residue at z equal to 1. So this is a pole of order 4. So we have 1 upon n minus 1 factorial. So n is 4 here, 1 upon n minus 1 factorial. So if you want, you can write formula first, but I will directly start here. 1 upon n minus 1 factorial means 1 upon 3 factorial. N minus 1th derivative means third derivative, d cube by dz cube. And we have to multiply by the same factor. So this is a z plus 1 raised to 4 into fz. So what happens actually, this z plus 1 raised to 4 gets cancelled with this denominator z plus 1. Okay, denominator, and always the as we are calculating residue for z equal to uh, sorry, z equal to minus 1 is there, my mistake. Residue at z equal to minus 1, so z plus 1 is a factor. Okay, so corresponding same factor always gets cancelled. 1 upon 3 factorial means 1 by 6 d cube by dz cube. One more thing I left, at z equal to minus 1. We have to calculate that at z is a minus 1. So z plus only e raised to 2z left. E raised to 2z at z equal to minus 1 we have to calculate at the end. So third derivative, first of all, we have to write third derivative of e raised to 2z. See, first derivative of e raised to 2z is e raised to 2z into 2. So third derivative is 8 times e raised to 2z at z equal to minus 1. And lastly, see, 8 by 6, 8 by 6 is a 4 by 3, and this is a e raised to minus 2. So that about the residue, and there is only one pole which is inside the circle, so that residue already calculated. Hence we get here the value of integral by Cauchy residue theorem. We can say by Cauchy residue theorem, the value of integral I is 2 pi I into sum of residue. 2 pi I into sum of residue. In this case, only one residue is there, so R. So 2 pi I into R. So if you replace the value of R, we get 2 pi I into 4 by 3 e square. I will take this e raised to minus 2 in the denominator as e square. So the value of integral is 8 pi I upon 3 e square. So this is the value of the integral without doing actual integration. We used Cauchy residue theorem and we got the answer. The value of integral is 8 pi I upon 3 e square. That is the way we evaluate the integral. Okay, so that about the first question. Most important thing where you should focus is whatever fz, whatever the integrand that were given, just focus on the denominator only. Check the poles which are inside the circle. If they are inside circle, calculate the residue and then use a formula 2 pi I sum of the residues there. So that about the question number 1. Now let me see some variations in the same example and what will happen. So the question number 2 is not new. So just focus on the question 2 now. Exactly same integral. Integral e raised to 2z upon z plus 1 raised to 4 dz is equal to, we have to prove this actually, 8 pi I upon 3 square. Already we got the same answer for previous question. For the circle, where the circle C is mod z equal to 3. Now already we observed that z equal to minus 1, this z equal to minus 1 is a pole of order 4, and that pole is in the circle of radius 2, so obviously it should be in the circle of radius 3 also. If we take any circle of radius greater than 1, strictly greater than 1, then the value of this integral always remains 8 pi upon 3, because there is only one pole in the denominator and that is already covered in that circle. So this is also inside a circle, inside mod z equal to 3, and if you calculate a residue here with exactly same calculation, you will get the same answer as a 4 by 3 e square. And once you get residue, you substitute as a 2 pi I. So value of integral is that is a 2 pi 2 pi I into sum of residues, 2 pi I into sum of residues, and you get the same answer, that is 8 pi I upon 3 square. So there is no change in calculation, only the first line will change. In the previous question we written z equal to -1 is a pole inside the circle mod z equal to 2, and here we written inside it is mod z equal to 3. Remember, the use of the equation of the circle is only to check how many poles are inside and outside. That is only the purpose of the we are taking the use of that circle here, and once we get that the poles inside the circle, we can get easily that answer there. That about question 2. Now question number 3 is something different. You will observe now the circle is given of radius 1 by 2, and we have the same pole. So z equal to -1, z equal to -1 is a pole of order 4, of order 4, but it is outside circle mod z equal to half. Means, therefore, fz, whatever the integrand we are given, is analytic on and within curve C. Hence, by Cauchy's theorem, therefore, by Cauchy's theorem, integration fz dz over the curve C is 0. No need to calculate residue. So this should be the answer for the question number 3, because there is no pole, or there is no there is no point where the function is not differentiable in the circle or on the circle, on and within the circle. Hence, the answer is a 0. That about the question number 3. This is the question 3. So any circle whose radius is strictly less than 1, the value of this integral is 0, and any circle of radius greater than 1, the answer is 8 pi I upon 3 square, greater than or equal to 1. So that are the two possible answers for this integral only. Okay, because of the Cauchy's theorem and Cauchy residue theorem. Next one is question number 4 now. If you see, the integral that we are given is a z plus 3 upon z plus 1 into z minus 2, and the circle given mod z equal to 3. Mod z is 3. So in this case, uh, uh, suppose we start uh, with the poles here. Here we have z equal to -1. You will observe z equal to -1 and z equal to 2 are pole of order 1. You can say pole of order 1, or you can say these are simple poles. Okay, any one. Pole of order 1. And whether both are inside or one is only inside, let me check. We are given mod z is 3. Circle is mod z is 3. And if you see the z is -1, that means mod z is 1. Z is 2 means mod z is 2. And their both mods are less than 3. So inside circle mod z is 3. So both are inside, so we should calculate the two residues now. So getting the residues for the simple pole is a very easy, because they have order 1, so no derivative required. Let r1 is a residue at z equal to -1. So if you take residue at z equal to -1, it is 1 upon n minus 1 factorial. Now see, n is 1. The order is 1 there. N is 1. 1 upon n minus 1 factorial is 1 minus 1 factorial. 1 upon 0 factorial. 0 factorial is 1. N minus 1th derivative means 0th derivative. Nothing is there. So nothing will left. So just we take this z plus 1. This is 0th derivative of z plus 1 into fz. But actually zeroth derivative means no derivative at z equal to minus. So we have to calculate this one. So if you replace z plus 1 into fz, in the same term gets cancelled. Z plus 1 gets cancelled. We left with z plus 3 divided by z minus 2 only. You will observe always that term gets cancelled. And we replace z by minus 1. So it similar to the shortcut method of partial fraction we discussed. So this is minus 1 plus 3 is 2 by minus 3. So minus 2 by 3. So R1 is a minus 2 by 3. Similarly, R2, now R2 is a residue at z equal to 2, second pole. So exactly same way we get z minus 2 into fz at z equal to 2. So z minus 2 gets cancelled. We left with z plus 3 upon z plus 1 at z equal to 2, and we get the value of R2 as 2 plus 3 is a 5 by 3. So we got R1 as 2 by 3, R2 as a 5 by 3, and now the final answer. So the value of integral I, therefore by Cauchy residue theorem, the value of integral I is a 2 pi I into sum of residues, that is R1 plus R2. So here it is a 2 pi I. The value of R1 is a minus 2 by 3 plus 5 by 3, and if you see the bracket sum is 1. So the value of integral is just 2 pi I. 2 pi I is the value of integral. Okay, so that is the end of the question here. We have here two different poles in this question. We have two poles actually, z equal to minus 1 and z equal to 2. Both are inside the circle. So whenever only those poles which are inside the circle, we should calculate residue for them and we'll add it. So 2 pi I into sum of residues gives us the final answer. So 2 pi I will be the answer for this question number 4. We come to the next here. Question number 5, similar to this only, exactly similar to this, only numerator is a different. So we have the same circle again, mod z is 3. So we can continue with the same, like here z equal to 1, 2 poles, order 1, inside mod z equal to 3. So both are inside there. So R1 is a residue at z equal to 1. So if we take R1 as a residue at z equal to 1, so we should multiply by the same factor, that is z minus 1 into fz at z equal to 1. So if we cancel that z minus 1 factor, we're left with e raised to 2z divided by z minus 2 and at z equal to 1. So the answer is e square divided by 1 minus 2 is a minus 1. So it is a minus e square, is it? Minus of e square. So that is R1. Now let me calculate R2. I will write it R2 as a residue at z equal to 2. I'll do little direct here. So we're left with e raised to 2z now upon z minus 1 at z equal to 2. I am written directly. You can check it. So if you replace it, e raised to 4 we get e raised to 4 upon 1. So that is e raised to 4 only. That is R2. So we got R1 and R2. So the value of integral now, the value of integral I is 2 pi I into R1 plus R2. This is by Cauchy residue theorem. So this is a 2 pi I. The value of R1 is minus e square and the R2 is e raised to 4. So yes, you can write the answer as a 2 pi I e4 minus e square. That way also you can write it, or you can take e square common, and that way also e square minus 1. So this is the value of integral. Okay, so that about question number 5. A very simple similar question. Next one, question number 6 here. Question number 6, again, yes, all these questions are very simple and easily you can get these 5 marks on these questions. Let me focus on the first bit only. If we focus on the first bit where we are given mod z is a 2, we can say z equal to 1 is a pole is a pole of order 1 of order 1 inside inside circle mod z is 2. So we should calculate residue then, because pole is inside a circle. So let R be the that residue. R is a residue where we say residue at z equal to 1. Residue at z equal to 1. So we'll cancel that factor. We're left with only that z square minus z plus 1 and at z equal to 1. If you replace all this, 1 minus 1 plus 1, so you get 1 only. So residue is 1. So by Cauchy residue theorem, the value of integral I is 2 pi I into R. So the answer is just 2 pi I. 2 pi I is the answer of the first bit. Okay. And second bit is very simple. In the second bit, we observe z equal to 1 is a pole of order 1 of order 1, but outside outside mod z equal to half. So because this is mod z is 1, so 1 is greater than a half, so obviously this pole is outside the circle of radius half. Therefore, by Cauchy's theorem, the function is analytic on and within the curve C. The value of integral is 0. Integration f z dz is a 0 on that curve. So that is the answer of the second bit. So just you mention all these things in the exam that z equal to 1 is a pole which is outside the circle, hence f of z is a differentiable function on and within the curve C. Therefore, the integral I is a 0. I is 0. So reasoning is also important. Just you should write in 1 or 2 lines there. So that about the question 6. Question number 7, little different now. Here, the main task is to get the poles of this function. In the question 7, we are given fz as z minus 3 divided by z square plus 2z plus 5. If we equate denominator to the 0, okay, if we equate the denominator to the 0, I will do some rough work on this side. So let I do here. So z square plus 2z plus 5 equal to 0. This is a quadratic equation in z and we want the roots of this equation to get the poles. So just denominator is equated to the 0. So by quadratic formula, z is a minus b, which is minus 2, plus or minus root of b square. B square is a 4, minus 4ac, 4, 1 into 5 is 20, upon 2a, upon 2a is 2. So it is a minus 2 plus or minus root minus 16. Minus 16 means 4i divided by 2. So we get minus 1 plus or minus 2i. Minus 1 plus or minus 2i. So if we start this side now, let alpha is minus 1 plus 2i and beta is minus 1 minus 2i, then we can get f of z. We can write f of z in this form. So f of z becomes z minus 3 divided by z minus alpha into z minus beta. So actually alpha and beta are the poles of order 1. Alpha and beta are the poles of order 1, but we have to check whether they are inside or outside the circle of radius 1. So we'll come to that. So here z equal to alpha, beta are pole of order 1. See the magnitude. If we calculate as mod alpha is equal to mod beta, because they are conjugate only, so which is square root of, see, mod of alpha is like x square plus y square, so 1 plus 4 root 5. Is root 5 less than or greater than 1? Root 5 is obviously greater than 1. Therefore, outside circle mod z equal to 1. As they are outside the circle, no need to calculate a residue for these. We can directly say by Cauchy's theorem, the value of integral, that is integration fz dz over the curve C, is a 0. The value of integral is 0 by Cauchy's theorem, because the function is differentiable on and within the curve C. This is the use of Cauchy's theorem. We can directly get the answers without doing actual integration. So the integration of that fz dz over the curve C on the curve C is a 0. That is the final answer. So that about question 7. We'll move to the question number 8 now. So question 8, yes, determine the poles of the function and residue at each point, hence evaluate. Okay, so whatever the situation, we have to find out poles, we have to find out residues first, and then we have to evaluate the value of integral over the circle of radius 2.5. So for this example, yes, we have two different poles now. We can say here z equal to 1, pole of order 2, and z equal to minus 2 is a pole of order 1, or we can say simple pole. So you have two poles. The question is find the poles first. So we written the poles first, that 1 and minus 2 are the pole of order 2 and 1 respectively. That is one thing. Now we have to calculate residue at each pole. So let R1 be a residue at z equal to 1. The question is find the residues also. So find residue at each point. So we are calculating compulsory like this. So to get the residue at z equal to 1, now remember this z equal to 1 is a pole of order 2. So 1 upon n minus 1 factorial comes as 1 by 1 factorial. 1 by 1 factorial is 1. N minus 1th derivative. So n is a 2. So n minus 1th means first derivative, d by dz of z minus 1 bracket square into fz at z equal to 1. So this is the formula. This is the formula of residue that we used. So z minus 1 factor gets cancelled. We left with d dz of z square upon z plus 2 only. Z square upon z plus 2. And then we are going to replace that z by 1. Now use a quotient rule. Use a quotient rule for the derivative, and then we can replace it. So denominator is a z plus 2 into derivative of numerator is a 2z minus numerator, which is z square, derivative of denominator is 1, upon denominator square, which is z plus 2 bracket square, at z equal to 1 then. At z equal to 1. So that calculation will do it here. So we are replacing z by 1 throughout. Okay, instead of simplification, 1 plus 2 is 3. 3 into 2 is a 6. So 6 minus 1 divided by 1 plus 2 is 3, and that 3 square is 9. So we get 5 by 9. You can check. 5 by 9 is R1. 5 by 9 is R1, that is residue at z equal to 1. Next is a minus 2. Minus 2 is also the pole. So R2 is a residue at z equal to minus 2. So in this case it is simple pole, so z plus 2 factor gets cancelled, and we're left with z square upon z minus 1 square, z square upon z minus 1 square at z equal to minus 2. At z equal to minus 2. So if you replace z by minus 2 here, minus 2 square is 4 upon minus 2 minus 1, that minus 3 square is a plus 9, so 4 by 9. 4 by 9 is R2. Now last thing, the question is hence evaluate the integral of fz dz on the circle of 2.5. If you see the 2.5 circle, both the poles are inside the circle because 1 and minus 2 will be less than 2.5. Okay, less than 2.5, their magnitudes. Hence, by Cauchy residue theorem, as they are inside the circle, 2 pi I into R1 plus R2. So that is the value of integral. So it is 2 pi I. If you do the sum, 5 by 9 plus 4 by 9, it is 9 by 9. And the answer is just 2 pi I. Okay, so that 2 pi I is the answer there. That is by Cauchy residue theorem. Okay, so this is the question number 8, where we got the answer as a 2 pi I only. Question 9, second last question only. Yes, I know the video is little lengthy, but yes, I will cover all the questions so that you will get an idea. If you have the doubts, you should clear it. Next one, f of z is sine square z divided by z minus pi by 6 bracket square. Now, this is the f of z given. So we have to find out the value of z first. Yes, we can say, remember throughout here, the value of pi you have to consider it as 3.14 and not in the degrees. It's a 3.14. So here z equal to pi by 6. Now what is a pi by 6? 3.14 upon 6, which is a 3.14 upon 6 is a pole of order 2, that is of order 2. Is it inside a circle mod z1? See, 3.14 upon 6, 3.14 upon 6 is definitely less than 1. So inside circle mod z equal to 1. So we should calculate a residue for it. We should calculate the residue for that. And the formula for residue, therefore R is the residue at z equal to pi by 6. R is the residue at z equal to pi by 6. So the formula is n minus 1th derivative. Now it is of order 2 pole. So 1 upon n minus 1 is 1 upon 1 factorial first derivative d by dz of the same factor we have to multiply z minus pi by 6 bracket square into fz at z equal to pi by 6. So this calculation we have to do it. So if we cancel out this z minus pi by 6 bracket square function, we left with the numerator only, which is sine square z. So it's a dz of sine square z only, sine z square or sine square z. Let us check. It is sine square z. Yes, sine square of z at z equal to pi by 6. Derivative of sine square z. Derivative of sine square is, yes, obviously derivative of x square is a 2x first. So 2 sine z into derivative of sine z is a cos z. That is a sine 2z. Sine 2z at z equal to pi by 6. So if you replace pi by 6, it is a sine of, if you replace that pi by 6 here, that it becomes a sine of pi by 3, because sine of 2z is there. So sine pi by 3, you should know the value. This is 180 by 3 sine 60. Sine 60 is a root 3 by 2, is it? Root 3 by 2. So it is a sine square z is there. Oh, my mistake. It is a bracket cube is there. Bracket cube is there. Okay, I started with a bracket square. Because of that, the answer is coming different. I taken a pole of order 2. If it is pole of order 2, it is sine pi by root 3 by 2 into 2 pi I will be the answer. Root 3 by 2 into. But here is a bracket cube is there. So let I correct little bit here, the corrections. First thing is we have that bracket cube is there. So is, okay, my mistake, just a minute, sorry. Here is a bracket cube, and this is a pole of order 3. Okay, everything will be wrong then. Okay, so there are many corrections. So we have to take 1 upon n minus 1 factorial means 1 upon 2 factorial outside. So 1 by 2 is outside, 1 upon 2 factorial, which is 1 by 2. And it is a d square by dz square of this. So second derivative we have to take it. So first derivative we already taken as a sine square z, sine 2z. So the second derivative we will take, okay, just a minute. Second derivative we have to write it. So the first derivative already taken here. So one more derivative left, d dz of sine of 2z left there, and d dz of sine of 2z, that is a cos 2z into 2. So 2 times cos 2z, that is the derivative of second derivative there. So first derivative we already seen, it is 2 times sine z cos z, that is sine 2z. And now you replace the value, it is a 2 times cos pi by 3. 2 times cos pi by 3. What is cos pi by 3? Cos pi by 3 is 1 by 2, so it is 1. So residue is coming 1. Hence, by Cauchy residue theorem, the value of integral is 2 pi I into sum of residues. So 2 pi I r, that is a 2 pi I into 1. So that is 2 pi is the answer of the question number 9. Okay, come to the last question, quick. Okay, this is the last question. We have to integrate tan z now. Tan z over the circle mod z equal to 2. So in this case, the integral I is given as, say, sine z. We should write in the fraction form always, upon cos z dz over the curve C. But C is mod z equal to t. Now, if you observe, cos z is a 0. If you equate cos z is a 0, implies z is, say, plus or uh, obviously plus or minus pi by 2, plus or minus 3 pi by 2, plus or minus 5 pi by 2, and so on. Out of that, pi is a 3.14. So 3.14 upon 2, 3.14 upon 2 is only the point which is inside the circle, because mod z is 2. Mod z is 2 and value of pi is 3.14. So 3.14. So there are only two poles. So we can say here z equal to pi by 2 and minus pi by 2 are the poles of order 1 inside a circle mod z is 2. So we have to just to calculate two residues, and uh, then we can get the value of integral there. So plus pi by 2 and minus pi by 2 is there. So obviously we should remove that cos z factor. Mm, and if we take sine pi by 2 and okay, uh, let me take r1 as a residue at z equal to pi by 2. We should cancel out that factor. Actually we should and these are simple poles, so it is just the remaining term. The cos z is creating the problem for getting or cos z is actually getting the poles there. So we left with only sine z there, sine z at z equal to pi by 2, that is 1. Similarly, you can get r2. R2 is a residue at z equal to minus pi by 2. So sine of minus pi by 2 we get as a minus 1. Okay, somewhere is a problem there. Sine of minus pi by 2 is a minus 1. Is that correct? Sorry. Somewhere there is a problem then. Huh? Is it coming correct? At cos pi by 2, these are pole of order 1. Is it? So in my case right now, if I go this way, the value of integral is coming 0, but the answer is given minus 4 pi. You can check in the textbook then, but right now the value of integral is 2 pi I into sum of residues, that is r1 plus r2. So 1 minus 1, that is 0. Okay, so if it, okay, I will check this question. If there is correction, I will tell you in the class. Okay, thank you so much. So that about your complex integration. Last two questions are not so important. Majority of the times the questions where these rational functions are given, they are coming like question number 1 to 8. Question 1 to 8 are mainly the important there.